Well, hello and welcome to part 10, is it? If it's 10, happy anniversary, everyone. To part 10 of an to-be astronomer who's currently writing his master's thesis and should really get going, is reacting to a geocentrist movie. They have last episode they delved into dark matter, and I thought that it would be just fair for me to give you an astronomer's perspective on dark matter. Now I talked about rotation curves, which were the first really strong important kind of evidence for dark matter. It was done in the 1970s by people like Vera Rubin, which I hope you know. She's really important. There's another guy, I believe he was Kent Ford or something like that. And they you can read all up on it. They did the thing with the rotation curves. I already talked about it. There are, however, so many other things that lead us to dark matter. I thought I'd mention some. There are velocity dispersions of stars, right? Stars that are in a system, they need to obey, if you will, the virial theorem. The virial theorem, I encourage you to Google it, is an equation that relates the kind of kinetic to the potential forces, really. And we every star that we know obeys it. It follows from theoretical predictions. It's kind of the same as with galaxy rotation curves. The thing is that the velocity dispersion of especially elliptical galaxies doesn't match the predicted velocity that we have for them unless they are way heavier than we can see that they are. So there's a hint at dark matter. There are also galaxy clusters. For galaxy clusters, which are essentially a whole bunch of galaxies bunched up, really. They're again the same thing with the radial velocities. We talked about that, but also from X-rays, right? From the X-ray emission, the X-ray emission of rather high energy photons, and we can estimate the temperature of the gas that is in between the individual galaxies in a galaxy cluster, because within a galaxy cluster there is intergalactic dust between them, because there's so much mass there that some gas is drawn into there, and way more X-ray emissions come out of there than we think that they should. So really, there needs to be more gravity there, kind of more things that create gravity than we think, but we can't see, which is dark matter. There's also things like gravitational lensing within individual galaxies, but also again on the galaxy cluster scale. They you know, when you have a whole bunch of galaxies and they create so much mass there that you can see that the light is bending around them, when you can see really strange things within galaxy clusters. We believe that dark matter is as much as 6 times as common as normal matter, really. Again, then there's gravitational lensing. Even the cosmic microwave background kind of gives us a hint at dark matter. We have the data from WMAP and from COBE, which are the two satellites before Planck that surveyed the cosmic microwave background. Even this data fits our dark matter ideas. I mean, the dark matter doesn't interact with light directly, but its gravity does, right? So yeah, it causes perturbations that kind of leave traces in the cosmic microwave background, and these perturbations can be seen if you know what to look for, really. Yeah, then there are things like the bullet cluster, which I can only highly recommend. This is 2 galaxies colliding currently, and from the bullet cluster we know that well, for example, okay, so 2 galaxies that are colliding, right? And they behave very differently from how we think they behave, which is curious. So the predictions that are made by general relativity in that case, they just don't work, which is curious because general relativity works on very large scales rather nicely otherwise. So either general relativity, for whatever reason, doesn't apply to the bullet cluster, or there is mass there that we don't see, right? All of these are kind of from calculations, if you will. Apart from the gravitational lensing, there is, however, something that I hold very dear, which is the that you can actually see them in kind of in radio astronomy, right? When you have okay, so in radio astronomy, sometimes we look at the 21 centimeter line of hydrogen, right? Which is 21 centimeters in wavelength, and that's why you can only see it with radio astronomy. And with that, we can see how much hydrogen is around, roughly. That there needs to be quite a substantial amount of hydrogen, so it's not useful for detecting small traces of hydrogen. But you can use it for very large scales, like when we talk about galaxies. And the thing is that when we look at galaxies, there is kind of the visible part that we can see, and then around there is what we call a halo of hydrogen, and we cannot really explain what keeps this hydrogen there unless there is stuff that we can't see there, like something that creates a gravitational force but doesn't interact with light, like dark matter. So really there are countless angles on which you can approach this. I haven't even mentioned things like there are things that go a bit more into detail, like some sky surveys that do things with acoustic oscillations. So many things. So we kind of know, or like we have very good evidence to suggest that dark matter is there. We just don't really know what it is yet. There are very many hypotheses about dark matter. Dark matter itself always also remains a hypothesis as of now. We just have substantial evidence and no better alternative explanation to get up with the thing. If tomorrow an astronomer or a physicist comes around and says, "Look, guys, I figured it out. It's this and that," and it lines up with the observation and it makes predictions that we can test for with observational equipment, and those observations holds true, we ditch dark matter. It's not like it's important to us. It's like, okay, then there's no dark matter. We were wrong. That's no shame in that, right? There are so many hypotheses about dark matter. There is some that involve completely different particles. Like there's one that's called the strangelet, which is made up of a particle that does strange stuff with strange quarks, which is a particle physics joke. Something where gravity actually works a bit different. Those are also ideas that you could have, right? There's the tensor vector scalar gravity, which I find interesting, although I don't really think it holds much water. There are quite a few hypotheses about how to explain dark matter. That there is something that only uses the standard model that we have. There are some that only use neutrinos, for example, because we still have problems with neutrinos. There are also those that say that, well, maybe it's only on a very small scale that dark matter is really relevant, but because there's so much of it, and all many things, right? We just aren't sure yet. But the point that flat earthers or like people bring up a lot is that, we only know like 5% of the known universe, but we know these 5% really fucking well. I apologize for swearing again. And the thing is that on Earth there is, as far as we know, no dark matter. The things like dark matter and dark energy and these things that are always being cited as, we didn't know about that they are almost not important to us. That's why we only had to come up with things like that, like within the last 100 years. That's why we don't know much about them. It's not like if there was dark matter relevant for any process that happens readily on Earth, right? We would. I am leaning out of the window and I'm saying we would know quite a bit more about dark matter than we do now. Now with this almost 10-minute rant of me finished about dark matter, let us actually continue.
Turns out the gravitational energy of every galaxy moving away from us is zero. And that's strongly suggestive that the universe actually came from nothing. In fact, every measurement we can make about the universe is really consistent with a universe that came from nothing.
What he wants to say here is that if you add up all of the known energies in the universe, right, and you add all of these up, and then you subtract all of the negative energies, for example, depending on how you define the binding energy of nuclei could be seen as negative because you actually need to put energy in to cause nuclear fission, for example, or you to split the atom, so to say, or the same holds for chemicals. You could give the bonding energy of chemicals a negative sign and things like that. And if you add all of this up, it appears to be rather close to zero. It doesn't. So that would kind of because creationists. This is really more of a creationist point now, right? Creationists often say that, well, no, the universe came from nothing, and that can't be because there's stuff here, and like, but you can kind of hit the number 0 with a hammer, and you get -1 and 1 out, neither of which are 0, but in the end you still have 0, so yeah.
Nothing, generally understood as the absence of anything, but sometimes used in modern cosmology to refer to an unseen form of something, virtual particles and the quantum vacuum.
Well, what we call nothing in our everyday language really doesn't exist in physics or in astronomy. Even when you take an area of space that is very much devoid, the intergalactic medium, for example, which is between two galaxy clusters in the middle of absolutely nowhere, you have like still one particle every cubic centimeter. But even if you pick a cubic centimeter where there's no particles in there, there's still things going on in there. There are virtual particles coming in and out of existence, as for example the Casimir experiment showed not too long ago, and things like that.
Something from nothing, a key concept in modern cosmology. But this turns out to be
I dislike the from nothing, because that implies that prior to the something there was nothing, which I dislike because time was created with the Big Bang. So you can't say it was prior to something because the concept of prior doesn't exist back then. So
a very unusual kind of nothing, since it apparently contains at least 2 somethings: energy and a law of gravity.
Well,
I like that the law of gravity is something, I guess, which why not put all of the other physical laws in there, and what's with the other fundamental forces? I mean, in the very beginning they were just one force, right? But what's with the other fundamental laws and forces? Apparently they're not important.
yeah, it's a strange time in cosmology. It's an interesting time because we don't understand anything, or rather, we don't understand nothing.
Yes, we don't understand nothing. That is very true.
Because it turns out nothing is almost everything.
If you understand nothing,
we have kind of not trouble, but we wonder if there can be something where absolutely nothing is going on, right? Where you don't have virtual particles in and out of existence all the time, or like this vacuum energy and things like that we haven't figured out yet. They're also really hard to figure out. But this responsibility is not with astronomy, because at the very, very fundamental level, this is a problem for particle and quantum physicists. So,
you understand everything.
Turns out the dominant stuff of the universe is nothing, and we don't have the slightest understanding of why. Nothing is really not quite nothing. Nothing is really a boiling, bubbling brew of virtual particles that pop in and out of existence in a timescale so short you can't actually see them. Now,
yeah, this arises with, not arises, but you can intuitively explain it with an uncertainty principle, right? Not necessarily the uncertainty principle, although that's also okay. Where you have the on the one side you have delta energy times delta time, and this needs to be at all times bigger or equal than 1/2 times the Planck constant, right? So really, what you're saying is that well, in the end, kind of, you have a perturbation that can be small enough in energy, for example, and if it happens at a large enough time and it stays smaller than 1/2 of the, I said greater than earlier, greater or equal, I meant smaller than, also, right? So that, and remains small enough to be smaller or equal to 1/2 of the Planck constant, then really it can happen. It kind of, you nudge it, if you will. It kind of, it really shouldn't, but due to the uncertainty principle, it can happen, right? So yeah, with that, we're already at 15 minutes. Again, I thank you for watching, and do all of the YouTube stuff that people are supposed to do. So thank you very much for watching. So you can kind of explain this with a bit of quantum mechanics, really. So this quantum energy, not quantum, vacuum energy, which is kind of the background energy, if you will, that exists like everywhere, just because it's there. This arises from really quantum field theory, where you have a field of, for example, an electron, like you have an electron field that is everywhere, and an electron is just like an excitation within this field, so kind of a wave traveling through this quantum field, if you will. And note that this is more of not really an explanation idea, but it helps calculate things, right? So the problem is that with that, every point in space essentially turns into a harmonic oscillator. And if you know a bit of physics, you know that harmonic oscillators in quantum physics have a lowest possible energy. You can't go lower than that in an harmonic oscillator. And the thing is now that if the things we know from quantum field theory, which by the way makes extremely nice predictions, those are really nice. This is essentially the state of the art when it comes to particle as well as quantum mechanics. So particle physics as well as quantum physics. You end up with quantum field theory at some point if you do that. So the problem is that you end up with the smallest possible energy, right? And the issue is that we would expect the zero energy to cause a very large cosmological constant, but it doesn't. It just doesn't. This is one of the current unsolved kind of high profile unsolved problems of physics. There are some ideas of what there may be around, one of which, by the way, is dark energy, I believe. I'm not all too much into this, because this quantum field theory is extremely theoretical, really, and it requires amounts of mathematics and formalisms that you need to know that are way beyond me. I'm not gonna lie, right? I did quantum mechanics. I tried to do advanced quantum mechanics at our university. However, this is one of the notoriously hardest exams you can do with our university, but now we have a new professor, so it may be okay. I haven't tried it yet with the new professor. I also did entry to particle physics, which was voluntary kind of, but with all of that, you don't even come close to getting at quantum field theory, which is, really quite a hunk. But I'm talking too much, right? So thank you very much for watching. Do all of the YouTube things that you do, and yeah, thanks a lot.